Alrighty, so today we are going to continue along with our introduction to calculus. We talked about the difference quotient last time, and today we're going to talk about something called limits. So we'll call today our intro to limits. Now, there are a few connections between what we talked about the other day and this idea of limits. I'm not sure if we'll get to a ton of it or really any of it now, but laying out these two ideas, the difference quotient and limits, if you do eventually get to calculus, you'll start to see where these two things are related. It's important to understand the concepts separately first before you can then start to kind of bridge that gap, which again, I don't know if we'll get exactly to that over the next couple of weeks, but we will see. So first of all, let's see if we can understand a limit. So I'm going to show you guys a series of pictures here, so we can make any of this bigger here. All right, so I was reading a website and a guy said, well, a lot of times the people confuse limits, making limits more confusing than they need to be. And a lot of people don't ever have a good conceptual understanding of limits. So let's take a look at this series of pictures here. So let's say you're watching a soccer game, and you see a guy, and he's got the ball close to the goal, and he starts to take a shot. As you can kind of see here, has the ball here, takes this shot. You can see the ball, and then all of a sudden the feed starts to buffer, and you lose track of the game for a second. But then when it comes back, you see the ball past the goalie, and then you see it going into the net. And you want to know, well, what happened to the ball during that time that it was buffering when you couldn't see it? Well, logically speaking, based on the fact that the ball was in front of the goalie before, and then after we got back from it buffering, it was past the goalie, we could assume that while it was buffering, it must have been going past the goalie. Okay. That would be a reasonable prediction that we could make based on what we're seeing both before and after this area where we can't see what's going on. Okay. So if we're kind of trying to put a definition to a limit, I would say a limit, and the most layman terms that I can give you is a limit is a reasonable prediction, of what's happening at some point based on what's happening around it. Okay, based on what's happening around it. Okay, so in other words, if we can look at what's happening both before and after, and we see a general trend happening in both directions, then we can assume that at that point in time, we know what's going to happen. Okay. Now, it's obviously not as clear cut and dry as this all the time, but this is a good way to kind of conceptualize this idea of a limit, which, similar to the difference quotient, is one of the foundations of actual calculus. So we're going to talk about two ways of evaluating limits today. One way, which you'll need a calculator for, is by creating a table. Okay, and another way is by graphing. Okay, so we'll discuss a couple of those today, and then as we move on into our future lessons, we'll also do some stuff algebraically and by looking at graphs as we go along as well. Okay, so let's jump right into one. Here's well, actually, I should probably lay out some notation for you first. So if you see some notation that looks like this, for example, the limit as x approaches 2 of, and we have some sort of function here. I don't know, let's say x plus 3. Okay, what this means is if you were to graph this, or if you were to look at this function, what's happening as x is approaching 2? So as we start plugging in values of x that approach 2, what happens to the overall value of this function? Okay, so that's what this notation means here. That'll be something new for you. So if we look at this problem, what this says is, what's the limit as x approaches 0 of this function right here, x divided by the square root of x plus 1 minus 1. Okay, now a reasonable thing to kind of think about, if you go back and look at this problem, I can take the number 2 and plug it right into this function. Okay, in other words, if I just wanted to say, okay, the limit as x approaches 2, well, why don't I just try exactly 2 and see what happens? Well, 2 plus 3 is 5. Okay, and if I kind of thought about what was happening, like, let's think here. If I plugged in like 1 and then 1.5, and then 1.9, and then 2, and then 2.1, 2.5, and 3. Okay, so in other words, if I plugged in all these x values into this function, what I would see here is 1 plus 3 is 4, this would be 4.5, 4.9, 2 plus 3 is 5, 5.1, 5.5, and 6. Okay, and what we can see here is from this direction we're approaching 5, and from this direction we're approaching 5. So we can see that the limit as we approach 2 is exactly 5, which actually happens if I plug in 2, I approach exactly 5. Okay, well, why not just use the same idea with this one? Why can't we just plug in 0 for x right here, similar to how it would have worked if I just plugged in 2 for this function right here to try to find the limit as x approaches 2? Well, let's try it. If I did just plug in 0, what would I get? I'd get 0 divided by 0 plus 1 inside of a square root minus 1, which would be 0 divided by, this is the square root of 1 minus 1. Well, the square root of 1 is 1, and then 1 minus 1 is 0. Okay, I cannot divide by 0. Therefore, trying to plug in 0 doesn't work. Okay, it doesn't work because I can't divide by 0. So we need another way of doing this that is different than just straight up plugging in the number. Okay, and a way that we can do that is we can create a table. It's not the only way to do this, but for right now, it's the only way that we know. So let's go ahead and try it. Okay, so what I want to do here is pick x values that get super close, but don't touch 0. Okay, because we just showed that if we do touch 0, then we end up dividing by 0. But if I don't plug in things that are exactly 0, I might be able to get a reasonable expectation of what's going on around there. I'm just not going to know exactly what's happening at 0 since that point doesn't actually exist. Okay, but remember, a limit is not exactly what's happening at a point. It's a prediction of what's going to happen at that point based on what's happening around it. So if I can figure out what's happening around it, then I can calculate this limit. Okay, so here's what I would like to do. First of all, let's pick some x values that are pretty close to 0. I don't know, maybe let's start with like negative 0.5, and then let's start getting a little bit closer, like maybe negative 0.1, and we'll try like maybe negative 0.01, and then we'll just try the exact same values on the other side of 0. So that would be like 0.01, 0.1, and 0.5. Okay, if I can figure these out, this is going to give me an idea of what's happening here as I get closer and closer to plugging in x equals 0. Okay, so this is where having a calculator is going to come into play. Here's what I'd like to do first. Let's go ahead and let's go to y equals, and let's actually plug in this function. So let's type this out here, x divided by, and definitely need to put parentheses on the bottom here. So the square root of x plus 1. So that's going to close out what's inside of the square root. Sorry, I don't need those parentheses. But inside the square root, and then outside the square root minus 1, and then I'm going to close the parentheses on the bottom of this function. Okay. All right, so I've got this function plugged in. We've done this earlier in the year, but you can go ahead and do this again if your settings have changed. If you go to second and table set, okay, up at the top, change your independent variable to ask, because what that's going to allow us to do is plug in these x values exactly. Okay, well, that'll let us plug these in exactly, and we can create this table ourselves, and we can fill in this table and then start to see, is there a general trend in which this function is approaching as we approach an x value of 0. Okay, so from here, I've got this set to ask. I'm going to go to second and table, and it's going to generate a table for me. Now, right now it's blank because I haven't asked it anything, but if I try to plug something in, well, then I'll be able to actually see what's going on the calculator. So for example, if I try to plug in 0, this is giving me an error. Why? Well, it's doing the exact same calculation that we're doing right here. It's the calculator's realizing, oh, if I try to plug in 0, I end up dividing by 0. Therefore, I have an error with that calculation. So instead of plugging in 0, let's try some of these values that we've picked. So negative 0.5, let's see, negative 0.1, negative 0.01, 0.01, 0.1, and 0.5. Okay, so let's take a look at some of these numbers here. Let's fill them in on our chart here. on the paper. So we've got, we'll round to like 3 decimals. So 1.707, 1.949, okay, 1.995. Okay, next one is 2.005, 2.049, and 2.25. Okay, so as we're looking at this, what's happening here is we are approaching from this direction. We're starting below 2, and we're getting closer to 2. As we're starting from this direction, we're starting above 2, and we're getting closer to 2. And it looks like from this table, we are approaching y equals 2, which tells us that the limit as we approach 0, as we approach an x value of 0 here, as I plug in x values that approach 0, that makes my y value for this function approach 2. So that is the limit as x approaches 0 of this function. And we can see that by looking at our table here. Our y values are approaching 2 as our x values are approaching 0. Okay? So that's one way that we can evaluate a limit, is just by creating a table and plugging in values that get closer to what it's asking me for here on the problem. Okay? All right, next one, let's try one with graphing. Okay, so this one says the limit is x approaches 2 of f of x, and it tells me that f of x is this function right here. Okay, now we have to dig back in our brains a little bit from earlier in the year to think about how to graph this. However, this is a squared function, which means it's a parabola. Okay, this is a parabola. So I'm going to go to the vertex of this parabola. -1 means go to the right 1. -5 means go down 5. So here's my vertex, and then it tells me that the stretch factor of this function is 2. So if you remember from the pattern of parabolas, this means you go over 1. 1 squared is 1 times 2 is 2. Back to the beginning, over 2. 2 squared is 4 times 2 is 8. So I'm going to go from -5 up to +3, because that's 8. So I get kind of a skinny parabola here. And here's my graph, okay? Now, this problem in particular is asking for the limit as x approaches 2 of this function, okay? So what that means is I want to see what's happening as I get closer from this side and see what's happening as we get closer from this side. And then I want to pick the y value that it's approaching as I get closer from either side. So as I approach from the left and as I approach from the right, I can see that this function is approaching a y value of -3. Therefore, my limit as we approach an x value of 2 for this function is -3. Okay, so there's a couple of examples of how you can either do this with a table, or if you want to, you can go ahead and graph the function and you can take a look at it that way, so we can see it visually through a table or either through a graph. Right. Another type of graphing one, let's take a look here, is this. Okay, the limit is x approaches 3 of f of x. But this time, instead of having a cut and dry function, we got something that looks a little weird, okay? This says f of x is equal to 2 as long as x does not equal 3. But if x does equal 3, then f of x is equal to 0. What does this even mean? I have mentioned this very briefly earlier this year in the first semester. This is called a piecewise function. Okay, and all that it means is this function is put together in pieces. It's not one continuous, or sorry, not continuous is the wrong word to use there. It's not one complete function the entire time. It's a couple different functions put together to create a full function, okay? So let's start out with this. F of x is equal to 2. That's like y is equal to 2, okay? And from your pre-algebra days, you should know that this is a horizontal line in which every point on the line has a y value of 2, and that is how this function behaves at every point except when x equals 3, okay? So let's go ahead and draw this here. What this means is y equals 2 for every point except exactly when x is equal to 3, okay? So I'm going to go ahead and put a hole there because that part of the graph does not exist for this piecewise function for y equals 2, but it does say that when x is equal to 3, y is equal to 0, which means that point actually exists right here, okay? So the only time when this function is not equal to 2 is when x is 3, and at x equals 3, then my y value is 2, okay? So this is a piecewise function. It has a hole in it, but now the question comes down to, what's the actual limit as x approaches 3 of this function, okay? Well, let's go back to kind of our definition that we came up with for a limit, okay? A limit is a reasonable prediction of what's happening at some point based on what's happening around the point. Okay, so what I need us to look at here is not what's happening at the point, but what's happening around the point. Okay, let's say, for example, that this whole part of the graph right here was blocked off. You couldn't see any of this, okay? But all you could see is what's happening as we get closer from the left and what's happening as we get closer from the right. Well, your prediction would probably be, should be, that as we approach from the left and we approach from the right, we are approaching a y value of 2, okay? Now, that doesn't necessarily mean that at 2, or that at an x value of 3, we are exactly at a y value of 2, okay? Doesn't exactly mean that, but what this means is what's happening as we get close to it. And as we get close to 3, we are approaching a y value of 2, therefore, this is the answer for the limit. Okay. Now, if I ask this question, what's f of 3? Well, this is a completely different question because this doesn't say what's happening around x equals 3. It says what's happening at exactly x equals 3. And this has a different answer because when x is 3, y is 0. Okay. So it depends on what's being asked of you. If you're looking for the limit, you're trying to figure out what's happening around it. If you're looking at some notation like this means what's happening exactly at that point. Those two things can be different and the limit can still exist as we see in this problem. All right? So what can we gather from that? Okay, the limit is the value we approach. It's not the actual value. Okay, and what I mean by that is in this particular case, we are approaching a value of 2 for y, even though the actual value at that point is 0. Okay, so we don't care about the actual value, we care about the value that we approach, which is why that limit in this case is not exactly what's happening at that point. Okay. All right. So one thing that I would like to note here, and this is another notation thing, if you see this notation, the limit as x approaches c from negative of f of x, okay, I'm going to say that this is equal to L, right? This means, what do we approach? Oops, sorry, I can't spell. What do we approach from the negative side? Okay, or in other words, what is that? What do we approach as we are coming from the left side? Okay, and limit as x approaches c from the positive of f of x. I'm going to call that r, which means what do we approach from the positive side? Okay, in other words, if we're approaching from the negative side, if we go back and look at this example, the negative side of x equals 3 would be all values that are less than 3. So we're trying to figure out what's happening in this direction. And then if we were doing the limit as x approaches c from the positive side, well, that means we're coming in the other direction from values that are larger than 3 as we approach 3. Okay, so this is a notation thing, but in order for a limit to exist, this is kind of a logical jump in thinking here. So in other words, in order for this, not distinguished as positive or negative, but just the limit as x approaches c in general, in order for this to exist, what must be true is that the limit from the left must equal the limit from the right. Okay? So if the limit as x approaches c from the negative side does not equal the limit as x approaches c from the positive side, okay, then the limit as x approaches c itself doesn't exist. Okay? So if we go back and think about this problem right here, because we were approaching the same value from both the left side and the right side, that means that this actual limit exists. Okay? It exists at a value of 2 because we're approaching the same value from the left side and the right side. Okay? However, if it looks something like this, okay, and let's say that this was an x value of, I don't know, 4, okay, the limit as x approaches 4 of this function does not exist because as we approach 4 from the left side, it does not match up with what happens as we approach 4 from the right side, okay? So let's take a look at an example like that. Then we'll finish out with doing some visual work. We're just looking at some different functions to close out for today. Okay, so I have another piecewise function here for this example. We have the limit as x approaches 3 of f of x. And for our function f of x, we have as x approaches 3, we have the function x minus 1 for all values of x that are less than 3. And then we have an x value, our function's value is 5 for all x values that are greater than 3, okay? So let's go ahead and start out with trying to graph x minus 1. That's a line, a linear function with a y-intercept of -1, and it has a slope of rise over run of 1. So we'll go up 1 over 1, up 1 over 1, up 1 over 1, down 1, to the left 1, so on and so forth. And if this was not a piecewise function, here's what this would look like. It would just be a continuous function that looks like a line like that, okay? However, it's not what this function looks like because it says this only happens for all x values that are less than 3. So what this means is I need to stop this function when I get to an x value of 3. And in fact, I can't actually put a closed circle on this because it doesn't say x is less than or equal to 3. It just says for x values that are less than 3. So I really need to put an open circle on that so that I can approach this problem correctly. Okay, now from here, the rest of this function says that for all x values that are greater than or equal to 3, y is equal to 5. So I have another horizontal line here starting at x value of 3, y is 5. Okay, so y will equal 5 for all x values larger than 3. Okay, so there's a graph of this piecewise function. Question says, does the limit exist? Well, based on what we just said on the last problem, let's see if we can identify a couple of these things. What's the limit as x approaches 3 from the negative side? Okay, well, if we think about it, that means what's happening to this function as we approach 3 from the negative side, which would be this direction. Okay, well, as we approach 3 from this direction, what we see is our function is approaching a y value of 2. Okay, but if we ask ourselves, what's the limit as x approaches 3 from the positive side? Well, that means we're coming from this direction. As we approach from the positive side, we are approaching a y value of 5. Okay, so the ultimate question here says, does the limit exist? Okay, well, think about it. From the left side, we're approaching 2. From the right side, we're approaching 5. Because L does not equal R, then this limit does not exist because we're not approaching the same value from either side, okay? So remember, in order for a limit to exist, you must be approaching the same value from either side of the function. In this case, we're not. So the full limit, the two-sided limits from both the positive and negative side does not exist, okay? All right, so my last piece of what I want to look at here is a picture, which I will post this along with the notes or along with the video, is this picture right here, okay? So let's see if I can go ahead. Actually, I don't know if I can do that. So taking a look at this picture here, let's see if we can answer some of these questions. Okay, actually, I am going to try to do this. Let's see if I can. Not that. Let's see. Okay. Okay. So we've got this picture over here for us to look at. And we have a bunch of questions for us to answer here in regards to the limits in this picture. Okay, now it looks like a lot. It's not going to be as long as you think. Let's just go through and let's start answering some of these. So f of negative 10. So what does this mean? This means when x is negative 10, what is y? Well, let's come over here. Negative 10 is over here. I see that I have a y value of negative 3. Okay. All right, next up, the limit as x approaches negative 7. Okay, we'll work our way down this way, and then we'll come over to these other columns. All right, remember, for a limit to exist, we must approach the same value from either side. Well, as we approach negative 7, from the left, we're approaching a y value of 2. From the right, we're approaching a y value of 2. So because those match, this limit is 2. Okay? All right, f of negative 4. What is what is y when x is negative 4? Well, I got an open circle here. I got a closed circle down here. I got to take the closed circle. So when x is negative 4, my y value is also negative 4. Okay. Now we got a couple questions here with one-sided limits, negative and positive. So let's take a look at this one. This means, what's the limit as we approach negative 4 from the negative side? Well, as I approach from the negative side, okay, I am approaching a y value of 4. Okay, but as I approach from the positive side, I'm approaching a y value of negative 4. Okay, I can see that there on the graph. So now, if I ask what's the question, what's the limit as x approaches negative 4, by taking into account the entire, both the left and right side, I can see that this limit does not exist because the left limit and the right limit do not match up. Okay. All right, next one, f of 2. So when x is 2, what is y? I've got an open circle and a closed circle. I got to take I got to take the closed circle. So when x is 2, y is 1. Okay, and then we once again ask the left and right limits. As we approach from the left side, okay, we are approaching a y value of negative 3. And as we approach from the right side, we are also approaching a y value of negative 3. So now if I ask the question, does the limit as x approaches 2 exist? Well, from the left side and the right side, it's the same. Therefore, it does exist, and that limit is negative 3. Okay, from both directions, I'm approaching a y value of negative 3. Okay, all right, next one, f of 6. Go over here to 6. Open circle, closed circle, got to take the closed circle, so I get negative 1. Okay, as we approach 6 from the negative side, I approach a y value of negative 1. Okay, but the next question says, what happens when I approach 6 from the positive side? As I approach from the positive side, I get a y value of, I'm approaching a y value of 2. So then if I ask the question, does the limit as x approaches 6 exist? Well, once again, left side, right side don't match. Therefore, the limit does not exist. Okay. And then the last question here says, what's f of 10? Well, if I go over here to an x value of 10, I see that I have a y value of 7. Okay. So this is a good quiz-like question here where I have to fill in some information about a graph that I'm looking at. In this case, biggest thing I have to remember is that if the limit is not the same from both directions, both the left side and the right side, then the limit itself does not exist. If it does match from both directions, though, the limit exists. And another thing is, just because the point has a value of, whoops, sorry about that. I'm sorry, no, it's good. Just because the point has a value, that does not mean the limit is that exact value. The limit is what we approach as we get closer from either side, not the exact value that we have at that point, okay? All right, so I will put up an assignment here soon for you guys to take a look at. I'll also post the notes along with this so you can kind of follow along there. Make sure you have a calculator with you. Let me know if you have any questions, okay?